Good morning and welcome to all the participants in this final day session 1 of this short-term training program on applied computational fluid dynamics for automotive, space and defense sector funded by AICTE under AQIS. Our today's speaker is Dr. Nagbhushan Rao Vatlamani. He is an assistant professor in Department of Aerospace Engineering at IIT Madras. Dr. Rao has received his PhD in engineering from University of Cambridge in 2014. Subsequently, he was awarded research fellowship by St. Catherine's College, Cambridge to pursue his independent research. He continued working as a senior research associate in the Cambridge University Engineering Department on Rolls-Royce and TSB funded projects. Prior to his PhD, Dr. Rao has worked with the digital mockup team in Airbus India on the safe installation of various aircraft systems. He pursued his master's degree in thermal engineering from IIT Madras and his bachelor's degree from NIT Warangal in mechanical engineering. Rao's research involves developing reliable numerical tools to build efficient components for the modern aircraft engines. In 2013, he and his colleagues were recipients of the ASME IGTI Turbo Machinery Committee Best Paper Award for their work on transition in low pressure turbines. His research areas include higher order methods and high performance computing, coupled interactions, flow control coupled interactions in turbo machines. Regarding his awards, he's received the research fellowship of Euro 1,20,000 by St. Catherine's College, Cambridge to pursue his independent research work. He was the finalist in Royal Academy of Engineering Research Fellowship in Literatureship at Oxford. In 2013, International Gas Turbine Institute IGTI Turbo Machinery Committee awarded him Best Paper Award presented by ASME. Regarding awards from IIT Madras, he has received Professor B. Senogupta Memorial Silver Medal for Best Academic Record in Mechanical Engineering and a Certificate of Academic Distinction and Silver Medal for Highest CGPA in first year in Mechanical Engineering. Thank you very much, Dr. Rao, for accepting our invitation, and you can start your presentation now, sir. Thank you.
Yeah. Thank you very much for the kind, introduction, Professor Maharshi. Am I audible to everyone?
Yes, sir, you're audible.
Okay, perfect. Thank you. So let me welcome you all aboard to this talk on turbo machinery simulations, progress and challenges. So this is, the idea of this talk is to give you an overview of all these 4 words, right? So we have turbo machinery, we have simulations, we have progress and challenges, okay? So for the next 1.5 hours, I'm going to talk about each of these in much more of a broader sense, okay? So I am not going to look into, one specific topic in great detail, but the objective of this talk is you will get a holistic picture at the end of the day, okay? So, and I have also provided references as and when required. So you can take a look at it, when if you want to look into any of the topics in greater detail. And feel free to drop me an email, and I'll be happy to assist you with any of your questions. And even during the talk, if you have got some questions, please feel free to stop me and ask the questions. Okay, let us keep it more interactive. So yeah, so the title of today's talk is Turbo Machinery Simulations, Progress and Challenges. And obviously the overview of the talk is I split those 4 words in the title into 4 different subsections, okay? So to start with, I'll give you a very brief introduction of turbo machinery. And obviously this in itself is a massive course which one would take. So let us confine ourselves to the basic understanding of a simple, a turbo machine, and let's restrict our discussion to the aircraft engines. Okay, so there are variety of turbo machines which are applied in variety of fields, but let's focus. The whole talk would basically focus on the aircraft engines. Okay, gas turbine engines in the aviation industry. Then we have simulations. So obviously, by simulations we mean computational fluid dynamics simulation (CFD). And there are, if you know some, like anyone who works on CFD, like there are a variety of options available to us. Okay, the way we resolve the geometry or model the geometry, the way we resolve the flow or model the flow, right? So there are a variety of options which are available, and I'll go through like some of these options which are available to you as a CFD practitioner. And the typical grid requirements which are required, like if you are talking about some high-end simulations, high fidelity simulations. Okay, so let's this terminology becomes more and more clear to you as we go through the talk. Then like in the third section, like we will get into the progress in this field, turbo machinery simulations. And over the last 10 to 20 years, there has been a really, like massive boost in the high performance computing facilities across the world, and how this HPC has actually transformed the simulations completely. Okay. So, and in that process, like we will also look at some of the case studies in which I was actually involved. Okay, so I did some of like the hands-on simulations of some of these components. So I'll share some of my experience, like in handling some of this multi-component, multi-fidelity, multi-physics simulations in, say, turbo machines. Okay, and finally, there are way too many challenges. The progress was, like is brief, but there are so many challenges which we as CFD practitioners and also, like in turbo machinery field, like we face. And as we move on through all of this, like I keep on like addressing some of the challenges, but at the end, I am also going to summarize some of the challenges. Okay, obviously it's a really exhaustive list, and I'm not going to get into each and every detail. Okay, right. So this is the overview of the talk. So let's start off with a background on turbo machinery. Is there some message or? Yeah. Okay. Right. So you usually encounter turbo machines in a variety of applications. The first one which you will see, like while boarding the flight, is a gas turbine engine installed right underneath the wing of an aircraft. So that's a simple aircraft engine, and you could have land-based engines, like which are used for the generation of power, right? So you could have a land-based steam turbine, like say Siemens is the largest manufacturer of such kind of engines. So where weight is not a critical issue, because it's all this engine is not flying in air, right? So whereas in the case of aircraft, like you should be worried about like the weight, right? So it should be light enough, and it should generate the required power. Then apart from these applications, you will also see some tidal turbines, like for renewable source of energy. There is a massive, like drift towards renewable source of energy, wherein there are many groups across the world working on tidal turbines to harvest the energy. Okay. And as we all know, like we also encounter this wind turbine, like and there is a lot of interesting physics involved in how to install these wind farms in open areas. Okay, so there are a wide range of applications. Of course, this is not an exhaustive list, but just to give you a brief idea of like where all, like even in space industry, like turbo machines are basically used for pumping the fuel and oxidizer to the thrust chamber of the rocket. But let's constrain ourselves to discussing the aircraft engine. Okay, so if you cut open that aircraft engine, like you see a nice outer casing and a lot of rotating components inside. Okay, so it looks a bit more complicated like inside, but to put it in simple terms, what this engine does is the outer casing is tries to supply really clean inflow to all the components. So this basic engine is it's simply breathing in the air, right? So it breathes a lot of air, and to give you the number, it breathes around 500 kilograms of air in 1 second, which is sufficient enough to make a squash court vacuum in a second. Okay, so it breathes in a lot of air. Okay. And the intake up front is trying to supply a very clean airflow. Like if there are some disturbances, it tries to die down in that little section like up front, and such that all these downstream components see a clean airflow coming in. Okay, so then it also consumes some fuel inside, like in the combustion chamber, and then we finally extract the energy because we have increased the enthalpy. We use that enthalpy to we convert that enthalpy available into some kinetic energy, and we extract that energy. And that extracted energy is again used to breathe more air. Okay. So if you look at the components which do these kind of this whole job, like the component which supplies the clean airflow is the intake. The component which is breathing huge amount of air is the fan. And the component which is consuming the fuel is the combustion chamber. And the component which is extracting the energy is the turbine. Okay. So for us, like the key turbo machinery components are the rotating ones. Okay. So turbine and fan, these are the key turbo machinery components. And also like we can't leave intake alone, because like any dynamics happening over this intake will also affect the fan downstream. Okay. So so the brief background is the turbine is the component which is extracting the energy. So there is energy already available in the flow, and the turbine is extracting the energy out of the flow. Whereas fan or compressor is like whatever energy is extracted from this turbine, that is being used by the fan, and that fan tries to add energy to the flow. It's very simple. Like turbine is extracting energy from the flow, and fan is adding energy to the flow. And this airflow passing through this engine is going to affect the performance of each of these components. Okay, so someone has designed, like all these components, and the airflow through this engine is going to affect the performance. Okay, and as turbo machinery engineers, CFD practitioners, right? So we are all interested in working towards a common goal. What is the common goal? We want to improve the efficiency of these engines. We want to save the fuel consumed by these engines and the associated costs. We want to reduce the weight, because this is a aviation based, engine. So you want to carry more payload, and the engine shouldn't be too heavy to do that. You should have the power to weight ratio. You should be maximized. You should generate more power, and the weight of the engine should be less. Okay. And apart from that, we should even noise is a pollutant. Okay, so it is absolutely annoying for those who are living right next to the airports. They get a really strong noise. So even noise is a pollutant, and there are so many teams across the world like working on this noise reduction principles. And of course, the most important thing is increasing the safety of this entire engine. Okay. And in order to do this, people do both the experiments and computations, and our discussion is confined to computations. And when we talk about computations, there are three key parameters which one should worry about. Like the first thing is accuracy. Is the computation whatever you are performing, or the models whatever you are using, are they accurate? And how fast are you getting the solution? So how quick the solver is. Right, so that is another critical parameter. And of course, you should not get some garbage values at the end of the day, right? So you should get some sensible results, and stability of whatever schemes you use is also another key criterion. So whatever solver you take across the world, these are the three metrics on which you can judge that solver. Okay, right. So that is the brief introduction about the turbo machinery, and what are common objective is. Now we just talked about the three key important points: accuracy, speed, and stability of a solver, right, while performing the simulations, right? So these are the three important points. And in this front, let us look at what are the different options available to us in terms of modeling the flow and modeling the geometry. Right. So if you open a tap in your house, you will see that if you marginally open the tap, then you will see that the water stream which is flowing out is very stable, and it doesn't have too many structures, and it's very well behaved, right? Or if you are dropping some oil, you will see that the flow is entirely sort of well behaved. So that's a laminar state. However, if you think of an engine which is breathing in 500 kg per second of air, right? So in 1 second, it's breathing in 500 kg, then you don't expect to see too much of such smooth kind of flow going inside the engine. You will see a lot of turbulence which is getting generated across all the components in the engine. So you see such kind of turbulence in nature, for example, say clouds, KH rollers across the clouds, or some agarbatti smoke, right? So you see some nice laminar region followed by transition to turbulence, and say even a candle plume, where you can see a nice candle plume, which is all laminar. Then there is some instability followed by breakdown to turbulence. And also the example of the wind farm, whatever I gave, like initially you see some structures like developing, but after you go further downstream, the flow becomes more and more and more turbulent. Okay, so each of these wakes will interact with the downstream wakes, and like it becomes a really complicated flow. So one thing which comes to our mind when we talk about turbulent flows is there is a lot of mixing involved. It's very rich in physics. There are a lot of spatial scales. This is varying very quickly in time, right? So in order to address this turbulence, like we have two approaches. One is you can model the turbulence, or you put a fine enough mesh to resolve the turbulence. Okay, so you let's look at these two strategies now. And the turbulence, like whatever I have shown here is some, turbulence encountered in nature. So similar things happen in turbo machinery components. For example, like over the turbine blades or on the compressor blades, you see a lot of chaotic flows developing. Say even on this intake lips and the fan blades, and like you could have shocks in the inside the engine over the intake lips or on the turbine blades, right? So you will have shock boundary layer interactions. So there is a lot of interesting and complex physics happening across all these components. And say over the intake clips, like you see some massive separations, and again, like it can generate a lot of turbulent flow. Okay, so turbulence, the basic takeaway from the slide is you also see whatever turbulence you're seeing in the nature, you also see them on the turbo machinery components inside that engine. Okay. So as I mentioned, like we have two approaches to basically model or resolve the flow. Flow is a turbulent flow, right? So in order to, so here I have shown a pyramid wherein like we have the different approaches, which I have highlighted here, say some steady RANs, unsteady RANs, hybrid RANs, LES, DNS, right? So this terminology, for those of you who are new to this kind of terminology, don't worry, like I'm going to just give some simple example so that like you'll understand this. And so there, the bottom line is that there are variety of methods, okay? And I have arranged this in the form of a pyramid. Now, like even for the geometry, right? So
Hello, sir, your audio is not coming.
this glass is entirely mesh resolved, okay? Whereas in the case of immerse boundary, is there some question?
Yes, sir. Your audio was not coming in between, but now it is coming from.
Oh, is it? Okay. Am I audible now?
Yes,
yeah?
Sir, you're audible.
Okay, thank you. Yeah. Okay. So say, so instead of, like putting a mesh around this glass, I say that, okay, there is a hypothetical glass here. And if I have a flow over this glass, we know that the flow should deflect, right? So instead of putting a glass, I can as well like create a hypothetical force there, right? Which represents the shape of a glass. Okay, so such kind of methods are called immerse boundary methods. Okay. So in turbo machinery, there is one more class which is called IBM-SG, which is immerse boundary method for smeared geometries. So we will look briefly at what that different interesting class of immerse boundary method is. Okay, but the bottom line is we have different methods for capturing the flow. We have different methods for capturing the body. And the bottom of the pyramid, like you are modeling the grid or modeling the flow. And on the top of the pyramid, you are either resolving the grid or resolving the flow. So when you move up the pyramid, you are increasing the accuracy of your final solution. Okay. Whereas if you come to the bottom of the pyramid, then you are decreasing the cost of the simulation. Okay. So you are compromising, these two are not going hand in hand. So of the two most important things, like for any solver, right? So we said accuracy and cost, right? Accuracy and quick, how quick these solvers are, right? So when you compare these two, like if you want really the amount of computational time like which it takes to give you that accurate solution is much higher. On the other hand, if you are compromising on that and you want a quick solution, then you are taking a hit on the accuracy. Okay. So, but the good thing, like which has been, like researched over the last 15, 20 years is, can we use some different combinations of each of these, right? So I will use some different strategies for the flow, different strategies for the body, right? So can I mix and match across this pyramid? So there are a variety of papers. If you go through turbomachinery literature, you will see a wide range of papers which are mixing and matching these sort of like flow, how they resolve the flow and how they resolve the body. But 20 years earlier, like everyone were at the bottom of this pyramid. Okay, so we didn't have enough computational power to actually hit this top of the pyramid. Okay, so accuracy versus speed, as I mentioned, is a trade-off. Okay, we have to, for whatever application we are looking at, like we should worry about like how much I can compromise on accuracy and how much speed will I get. Okay, right. So in terms of the flow, let's look. So as you move up the pyramid, if you take a simple flow past a cylinder, and as you are moving up the pyramid, the kind of simulation, the kind of flow which you would visualize is going to change like this. So if you start from a simple steady Reynolds average, Navier-Stokes, so some simple steady simulations, like there you will see some nice well-behaved vortices. But as you keep on increasing the resolution of the grid, whatever you use, like you keep on, like capturing more and more and more features of the flow. So you are resolving more and more and more features of the flow. So, and I am assuming that everyone like who has done a course on fluid mechanics, like they have come across something called Navier-Stokes equations, right? So you have the continuity equation, then 3 momentum equations and energy equation. So if you take those 5 equations and solve the flow past a cylinder at high Reynolds numbers, like exactly, then you might get a solution something like that, where you are resolving all the scales of turbulence. Whereas if you say, hey, I don't want to, resolve all the scales, I will do some modifications. I will simplify this Navier-Stokes equations. I'll average them, I'll do some Reynolds averaging, etc. And then, I mess up those standard Navier-Stokes equations. And, I introduce some new modeling terms into the solution. Then what you end up getting is, a steady Reynolds average Navier-Stokes equations, or if you relax some of those modeling constraints, you will end up with unsteady Reynolds average, right? So, but you clearly see the distinction, like as you are moving up the pyramid, you are resolving more and more and more. Okay, so what are all these structures which I'm showing here? So these are nothing but vortices, right? So you had on day 2, like Professor Samin, like he introduced you to vortex dynamics and how they were capturing some axial vortices. So all this turbulence is characterized by a lot of coherent structures which are called vortices, right? So you can imagine these vortices as some bunch of fish of different sizes. Okay, and if you want to capture this fish, what will we do? Like we simply put a net on them, right? So similarly, like in a turbulent flow, like if you want to capture all these vortices, like you simply dump like a fine enough mesh. Okay, so now at each and every point on this mesh, you are going to satisfy this highly coupled nonlinear equations, which are the Navier-Stokes equations. Okay, so if you resolve all the fish, right? So up to the smallest size of this fish, if you have put a fine enough mesh that you are capturing even the smallest fish or the smallest vortex in your system, then it's called a direct numerical simulation. If you say, hey, I really don't care about, like all the small vortices, maybe it is not contributing much towards my accuracy. I would rather, capture only the large fish or the large vortices. Those, and like I can dump some model like which says, okay, this much of energy is being carried away by vortices which I'm not resolving. Okay, so such kind of approaches are called large eddy simulations, where we are only capturing the large scale vortices and the which means large scale fish. Okay, so this is a very a brief idea about like the pyramid, like the way of capturing the flow, how that goes. And over the recent years, there have been many tests which have been done from the bottom of the pyramid and from the top of the pyramid, different approaches. Okay. So what they have observed is, this is a simple example of a labyrinth seal used in a turbo machine, near the high pressure turbine region, where they wanted to measure some radial variation of some velocity. Okay. They used so many different models. Okay, so on the bottom of this pyramid, people came up with so many different models, and this is quite a challenging flow. And there are many models, like say K epsilon, RNG, RSM, SST, different varieties of SST, right? So, but what you can see is, when compared to the experiments, you see a large scatter in the results. Okay, so the reliability, the accuracy, is obviously taking a hit here. And the models, whatever are developed, are not applicable for all the flow scenarios. Okay. Whereas if you are increasing the resolving component, say even if you are going up to say wall resolved, say LES, you see predictions has decreased. Okay. So the community is more and more shifting towards resolving the simulations more rather than modeling. Okay. Now, how much can we resolve? What is that, those scales, whatever we are generating, what does that depend on? That obviously depends on how fast the flow is moving, right? So for example, that is quantified using the standard Reynolds number, right? So Reynolds number, we know, is the ratio of the inertial forces to the viscous forces, right? So if the inertial forces, which means if the velocity or the length over which the flow is happening, if it is really large, then it is going to obviously generate more and more and more vortices. Okay, more and more turbulence is getting generated over that. Okay, so here you can very clearly see the distinction. This is at a higher Reynolds number, and the simulation on the top is at lower Reynolds number. So you can very clearly see that this simulation, you see much more finer scales, than whatever scales of vortices you are seeing here, right? You can even see some shear layer, these are much larger when compared to whatever very thin vortices which you are actually seeing here, right? So as you are increasing the Reynolds number, the number of vortices which you are generating is becoming proportionally, it's increasing proportionally. Okay. So higher the Reynolds number, the wider is the range of spatial scales and temporal scales which we have to resolve. Okay, and what does that mean? We have to put more and more mesh into it. So as a typical estimate, again going back to the pyramid, on the top of the pyramid, we need almost Reynolds number power 2.6 is the total number of grid which you have to put to capture the flow accurately. If you are introducing more and more and more modeling, that's when you keep on reducing this exponent. Okay, so if you have to do so whatever simulation I have shown is only on one little component. Okay, and that's where we spend a lot of mesh. But if you have if you want to do some multi-stage simulations where you have a fan, you have a turbine, you have a compressor, combustion chamber, right? So the kind of meshes which we are talking about is of the order of 1 billion plus. Okay, so and in this situation, it is not just we can't write as a derivative in our Navier-Stokes equation, say partial u by partial x. I can't say, if I write it as ui plus 1 minus ui minus 1 divided by 2, that is only giving me second order. Okay, there if we can actually make it a higher order stencil, go up to 4th or 6th order, then we can actually capture more detail using less mesh. Okay, so and that's where all the schemes, high order schemes, are also getting used in the modern day solvers. Okay, so they want to increase efficiently use the computational resources to capture these flows, and that's where the high order schemes are also playing a really big role. Okay, so to just put that, this n whatever we have, if you go for high order schemes, this can drop further. Okay, so now if you look at the grid count which is required for different turbine zones. Okay, so I talked about the turbine which was extracting the energy. So that turbine can be a low pressure turbine, further down in the engine, or it can be a high pressure turbine which is further up, right? And there could be some cutback trailing edges. There are some cooling ducts. There are some, rim seals or labyrinth seals, right? So there are different components in that turbine, right? And each of the Reynolds number at each of this component is completely different, right? So it is, the grid count is absolutely like different. So this plot nicely puts, as when you are talking about different components, like as we bump up the Reynolds number, what is the typical grid count like which we have to put to resolve the flow accurately? Okay, so there is an estimate like which has been given in literature. I'm not going into the details of how this is done, but there is some sort of like a reference like where you can see, hey, like my Reynolds number based on some chord of the aerofoil and some inlet velocity is so and so. And you can look up this specific chart and say, okay, yeah, I need to at least use a 10 million mesh if I am talking about large eddy simulation, or if I use some other modeling strategy, hybrid Rensselaers or something, like I can choose different strategies also here, right? So this is what the chart is basically given. And the current capability like across the world is like we can go up to say a billion cell calculation, which is huge. Okay, so this was never the case, say 20 years back. No one would have thought of running a billion cell calculation. Okay, so but still, like with this current capability, we are still going to handle only stage level. But if you want to kind of capture the entire engine, like you are talking about 10 to 100 billion grid points to capture the entire engine in great detail. Okay, so that is all about like modeling the flow. Now, when it comes to modeling the geometry, as I mentioned, there is this interesting bit called IBM SG, immerse boundary method for smear geometries, which is particularly relevant for turbo machinery. For example, like if there is a fan, like you want to know like the force field over all this, like all this blades, right? These blades are spinning at a really high speed. Okay, so when these are spinning at a really high speed, like we can make an assumption that I can consider this blades to be infinitely thin, and like the circumferential variation of the force field can be neglected. So under such conditions, I can come up with some axisymmetric geometry wherein, so what does this blade do? The blade is taking the flow axially and it is turning that flow by some angle, okay? And I should somehow hypothetically create that deflection by using a force field, okay? So, which means we are smearing off all these blades. There will be no blade at all. Okay, so we will not consider any blade, but we will create the effect of the turning by means of some body force. And that body force is going to be circumferentially, it's going to be uniform. So whatever force is seen here is the same force seen here or across any angle. Okay, so this is called a smear geometry. Okay, I'm not considering individual blades, but I'm considering the overall effect of the turning of these blades at high speeds. Okay, so then we can proportionately get how the pressure is increasing in the duct. Okay, so the flow is entering axially. There is absolutely no blade here. Okay, but we have replicated the effect of the blade using some body forces and the smear geometry because it's spinning at really high speeds. Circumferentially, we are saying that we are ignoring the circumferential variation of this force, which in some cases might not be true, but in most of the cases that will be true. Okay, so the pressure rise across the fan, you can very clearly see the role of this fan is to increase the pressure, right? So you are taking the flow at low pressure and you are bumping up the pressure across the fan. So that is basically obtained just by using the body force. So this is one aspect of modeling the geometry IBM SG. Then the other issue is, all the simulations which we currently carry out, they all assume that all the surfaces are absolutely smooth, right? And that is only true like when some manufacturer, he simply deploys the blade. Okay, so when it comes out of the manufacturer, like you see that it's all very smooth, it's amazing, right? So it's all very smooth finish and it's all fine. And all our analysis, whatever we have done on smooth meshes is valid for that. But now this is a high pressure turbine blade and this sees so much of high temperatures, say something like 1700, 1800 Kelvin is coming and hitting this blade, right? And as the engine keeps on, as you keep using the engine, you have so many flights happening per day, right? So it goes through a lot of cycles of operation. And then, you take that blade after 1 year and this is how it looks, okay? So it is completely rough, okay? So you have to also, the current simulations are also trying to look at the effect of this surface roughness on the aerodynamic characteristics of this blade, okay, that in-service degradation. How is the performance going to degrade as these blades keep deteriorating in time, okay? And if there are some complex geometries, then also you can use something called sharp interface IBM, or here you can also go for mesh resolved approaches, like where you put a finer mesh around the body, okay? So as I mentioned, like in this specific case, it's a toy case which I tested, wherein I use some wall model LES or a hybrid Grants LES for the flow, and I used a sharp interface IBM for representing the body. Okay, so you can you can appreciate the features of the kind of turbulent flows, like which ejects from that whole simple geometry. Okay. So that is all about the simulations. Okay, so in simulations, what we saw was like what are all the options which are available to us. Okay, so in terms of and how much fine the grid which I use for this simulation should be. Right. Now let's get into the third aspect, which is the progress. Right. So the progress actually started, and it has taken a steep rise in terms of the turbo machinery simulations ever since the advent of high performance computing. Okay. So parallel computing is the key for the progress of, like whatever progress turbo machinery field has done in the last 20 years, like HPC plays a major role, okay? So it is not sufficient enough for you to be an expert in turbo machinery alone or fluid dynamics alone. You should be an expert in fluid dynamics, you should be an expert in turbo machinery, and also HPC, like which involves like a lot of computer science and, like how you, optimize your solver, right? So let's look at what happened with the HPC in the recent years. So if you take any simple case, for example, this is an intake, right? So this is the outer housing, like and this is the spinner, right? So there will be a fan downstream here. In this simple mesh, I'm not showing any fan here. But all that you will see is this is the intake. Okay, so this is the intake lip. The flow is coming like that. Okay, and in fact, like it takes a turn and it enters like that. Okay, when you simulate a crosswind, etc. But this is the spinner. Okay, so this is the spinner. This is the intake lip. So in any CFD, the typical pre-processing steps which you do are like you generate the grid, right? So once you generate the grid, you give it to the solver, where the solver is going to read this grid. This grid can be structured as shown here, or it can be unstructured. Okay, and usually this grid is in the order of millions. Okay, so many points. So this is the mesh which I'm talking about, like to capture all the fish or the vortices. Okay, and then you set different boundary conditions on all this boundaries, and then what will you do? Like if you are talking about a billion points, or even say 30 million grid points. Okay, and if you try to run it on your laptop, what happens? Can you run 30 million grid points and solve all these 5 equations on your single laptop? Can you?
No.
No. Why? What limits it?
Processor.
Processor. And what component of the processor limits it?
Code distributions.
Fine. And can you store all this information in your brain? You can't, right?
No, yeah.
So what is it? Memory, right? So similar to us, like even a computer is limited by the amount of memory it has got, right? So it can't store like all this millions of grid points in its memory. So in order to solve this problem, what should we do? Like we should rely on more number of computers. Okay, so that is a distributed memory parallelism, right? So each computer has got its own memory, and all that I will do is I'll split this grid. Okay, I'll split this grid into a number of blocks. So now, like the amount of memory which a computer has to work on, the amount of work assigned to each computer is limited, and that is limited by its memory. And that memory is, like according to that, like we can split this block. Okay, so we create different blocks. And now, like if you look at the close-up view of this block, you will also see some overlaps here. Okay, so we are actually having some ghost cells to get the information. We are peeping into the other block to get some more information and maintain some high order accuracy. Okay. So we are literally like splitting, we are domain decomposing. We are decomposing this domain into multiple blocks. Okay. And each computer will get its share. Okay. Now what should the computers do? So if I'm solving the Navier-Stokes equations, I want to see like at some time instance, I will stop the flow. Okay. I will stop the simulation. I will pause the simulation. I want to see the flow on this. Right. So then what should the computers also do? Is it sufficient if they simply compute all the Navier-Stokes equations in just the box assigned to them? Is it sufficient? Yeah.
No.
What else should they do? What is their other job?
They should also store the data.
Yeah, or across the interfaces, right? So across these interfaces, they have to store the data, and they should also talk, right? So these computers also have to talk with each other, saying that, hey, this is the interface data which I have. This is relevant to you. And the other processor also says, yeah, I have some information from my end, like which I have to share with you, right? So each of these processors also have to talk, right? So they compute and they communicate. So there are two aspects to this. So ideally, like we will get a good speed up, and like we can solve this problem properly. Like when if this problem is put on a single computer, say if it was possible to put this on a single computer, then we finish the job in say some one day, right? Now I put the same job on 24 computers. I should expect to get the job done in 1 hour. That is the ideal scaling. Okay, but will we get the ideal scaling? We don't, because it is not just computing. Okay, so they are not just computing alone. They are also talking, right? Because they are also talking. If each computer is independent, then it's fine. You will get that nice 24 hours, like 24x speed up. But because there is communication involved, like you will not get a 24x speed up. So if you take this domain and keep on decomposing more and more and more, what happens is something like this. So here I am dumping almost like 1600 processors for that problem. And surely I'm not getting that 1600 speed up. I'm actually getting only 800 speed up. Where is the other speed up gone? That speed up is gone, because the job, whatever the computation, whatever they are doing, the computers are doing has decreased. The amount of talking which they are doing has increased. So the communication has increased and computation has decreased. So this is the bottleneck, like which one would hit when you are talking about message passing interface. So this whole process, whatever I told you, is nothing but the message passing, okay, between the computers. So you can parallelize any of your solvers using this, but you will also at some point you will end up with this computation versus communication issue. Okay, what is the other strategy? The other strategy is there is one massive memory. I give one big memory, like which is a shared memory. All the processors, whatever data all these processors require is put into that memory. Okay, so that's a shared memory parallelism. And one of the really interesting recent developments in this front is the use of GPUs. Okay, so GPUs are the graphical processing units. Traditionally, they were introduced for gaming purposes. So if you are a really good gamer, like you want to have good graphics, right? And you would have bought some parts, like your computer would have got an NVIDIA graphics card, right? So all that it does is it's a co-processor. Okay, so when your game is running like that, okay, and then like it sees it's a code. The game at the end of the day, the game is a source code. Okay, so there is a code in the background, running in the background. So when the game is running on the CPU, it encounters some really computationally intensive loop. Okay, so which is really a CPU takes so much of time to actually run that loop. And that kind of loop, you can dump it onto GPU. You say that, hey, like this is a really computationally intensive loop, and I want the GPU to perform this. Okay, so then the GPU is going to do that much faster, because like there are so many cores. Okay, so there are many small cores which can almost like 3000 odd cores in the modern V100 GPU card, which accelerate the application. It accelerates that green portion of the code. and says, hey, this loop has been computed. Now you go ahead with the CPU computation. Okay, so that data gets transferred back to CPU, and then the game runs further. Okay, so but here also we have another issue. So CPU has its own brain and GPU has its own brain. So CPU has to transfer whatever has its in memory to the GPU, and then only the GPU will compute, and then whatever has been updated in its memory will be transferred back to CPU. So that's how this whole system works. And we don't want to have too much of this data transfer, because again, these two are talking. CPU and GPU are talking too much. So under such conditions, then again, we will hit the performance. Okay, there is a performance penalty. So it is a similar issue which we had in MPI. All the process at some point they keep talking and do little work. Okay, so the latest strategies are again, like the GPU is also limited by the memory. Like you can only put up to some 15 to 20 million grid points, but whatever we are talking about is of the order of billion, right? So you need more GPUs, and also like you need more CPUs to handle them. So that's where this hybrid parallelism is one of the recent like progress like which has been happening in the field, right? So where you use both the MPI parallelism and the GPU parallelism, and each computer, like each CPU would be assigned to one GPU, right? Or maybe 3 or 4 CPUs will be assigned one GPU to help them out in carrying out this high intense computations. Okay, right. So now, like with such kind of architectures, here I am showing how this computing power has increased over time, right? So from 1990 to 2030, and here I am putting the floating point operation per second. So in your say, like once you read the grid, you want to compute the volume of each of the cell, right? So there are a lot of multiplications involved. There are a lot of additions, subtractions. There are a lot of things involved, right? And each of them is counted as a floating point operation. So, and this number is telling like how many floating point operations can be done in 1 second with the current, like with how did that evolve over the last, 30 years or so. Okay. So traditionally, like say in 2000 or something like that, we were only able to carry out simulations in Turbo Machine, like which could handle just a little section of a blade. Okay, so a very small section of a blade that could be done using some eddy resolving approach. So you are on the top of the pyramid, but with that you can only handle one little section of the blade. And with the current scenario, like you can very clearly see here, there are some rotors, there are 2 or 3 rotors, there are 2 or 3 stators, right? So you have some rotor blades, you have some stator blades, right? So in turbo machinery, you have some stationary blades, and then like you have some rotating blades. Okay, so you can these two put together is called a stage, right? So you can at least go up to a single or 2 stage calculations with the current computational facilities, right? So 1 to 2 state simulation. So you have some rotor stator sort of like arrangement. So you can go up to some 1 to 2 state simulations with the current number of computing capability which we have. So, and that is like 10 power 15. Okay, so currently we are talking about, say, if you look at the cluster in CDAC, Paramshawak, or that's Kharagpur, I think. Yeah, but I forgot the name. But yeah, so if you look at that computer, like it's of that workstation, sorry, that HPC facility is almost of the order of like say 5 petaflops. Okay. So which means it can do up to 5 into 10 power 15 floating point operations per second. So 5 into 10 power 15 additions or subtractions in 1 second, right? So that is the kind of, speed which we are actually talking about, right? So, and that is what and this is still really thirsty. So this is our current capability. And with this, we are only able to handle 1 to 2 state simulations. But if you talk about much more, engine type simulations, like it is still beyond the reach. Even till 2030, we are only talking about exaflop, so 10 cube increase. But whatever this entire handling the full turbo machine, it requires much more, computing power. Okay, right. So let's briefly look into some of this case studies. So where I'll just give you a idea of in terms of the progress, this is how HPC was has developed, and how did I personally say use HPC to run some of these simulations is the next part. Okay, so in that context, like I'll just look at some of the transitional flows. This is a low pressure turbine flow in a low pressure turbine. And then like there is a fan and there is an intake. These two keep interacting, like the fluid dynamics happening on the intake can adversely affect the fan, and so and vice versa. And you will, as I mentioned, you are also you should also worry about the sound which you generate, right? So what is sound in terms of pressure? Sound is nothing but a pressure fluctuation, right? So when you hit something, like you are making sound because you are generating some pressure fluctuations. And that pressure fluctuation is what like you are hearing with your ear as sound, right? So now whenever this fan blade, this fan blade is rotating at really high speed. Okay, so this one up front is the fan blade. Then downstream of this engine, like you have two stators. So this is a rotor, and downstream of that, we have two stators. One is a bypass duct, a stator in a bypass duct, that is called the outlet guide vane. And there is a core flow, like there is another stator inside the core duct that is called the engine section stator. So when this fan is rotating at really high speed, similar to a flow past a cylinder, behind the cylinder you see a wake, right? You see the wake and you see the wake shedding, right? Similarly, like downstream of the fan, you will see some wake shedding, okay? And when that wake comes and hits these components, it generates pulses of pressure, right? So you get pressure fluctuations. Like if I'm hitting this wall, like with this one, like I'm creating some pulses of pressure in the surrounding vicinity. So similarly, whenever this wake comes and hits this fan, like the downstream blade, it generates pulses of sound. And that gets, transmitted upstream, downstream, it travels in all directions. There is, it's a spherical sort of like a front, right? So it travels basically in all the directions. And even noise, as I mentioned in my first slide, it is a pollutant and we should control that, okay? So there is something on the aeroacoustics, and finally there is some solver development, like which we were really actively involved in. So me and my group here are really actively involved in developing this high fidelity solver. Right, so let's look into this transition in turbines. So the first component is the turbine. So as you can see, this is there are so many blades within this turbine, and the weight of this entire engine is almost like 6 tons. Okay, so you can imagine like one engine is weighing 6 tons, and like you have 2 engines. If it's a A380, you have 4 engines, and you're talking about 24 tons just of the engine weight itself, right? And of that entire weight, the turbine which is extracting the energy is contributing to 30% of that weight. Okay, so almost like 7 tons of the, say, A380, like 7 tons is turbine itself, right? And say if you want to reduce the weight of the engine, that is the aim. Then what should we do? Like the simple solution is we get rid of the blades. Okay. So it's like you are an employer, right? And you want to cut down the cost of the company. So you simply remove the employees, right? So when you do that, like what happens? What should you do? In order to, will your company work? It is not going to work because the workload is still the same, right? So then you should overburden the employees you currently have, right? So something similar happens in a turbine blade, right? So you have some older designs, like wherein, because you turn the flow, and while turning the flow, the angular, the change in the angular momentum is converted into the rotational kinetic energy of the flow, right? So Euler's equation, right? So I'm not going into the details, but the whole idea is when you turn the flow, like you are extracting the energy, you are decreasing the enthalpy available across the flow. You are extracting the energy from the flow and converting it into work, right? So you are producing work, you are rotating the turbine, and this turbine is connected to the fan up front, right? So the older designs, you can very clearly see they used to turn the flow to some extent, whereas the modern designs, these blades are much more steeply turned, okay? So, which means they are trying to extract more work out of the flow by turning the flow much more, okay? So, in this process, like these are called highly loaded blades. And obviously, like if you overburden an employee, what will happen? Like he is going to break down at some point, right? So, something similar happens in the this modern designs also. So this there will be, the flow is going to start laminar here. It is going to separate out because it can't overcome the adverse pressure, local adverse pressure gradient here, and it quickly transitions breakdowns to turbulence. Okay, so you can very clearly see that this, if you follow the edge of the flow, that flow is still trying to go back to the original blade design only. Okay, so whatever extra thing, like whatever we have provided, it is not sufficient enough for the flow to actually, like follow that blade. It is simply detaching from the flow, right, from the blade, right? So now what can we do? Like we have to give some incentives, we have to give some energy to our employers so that they can handle this sort of like a load, right? So under such conditions, like, and please note that this turbine blade is somewhere further downstream in the engine, right? It is not even, like it is not the first component which the flow is seeing, right? So this is further downstream in the engine. So which means like you will also have so much of turbulence which is generated by upstream components coming and hitting this. You will also have some rotors or stator wakes, like all those things coming and hitting this blade. And as I also mentioned, like when this turbine blade is deployed, it is very smooth, whereas like with time it degrades, right? So there is surface roughness, right? So you have all these three basically affecting this turbine blade, right? So it is not just the problem of flow separation and transition to turbulence, but it is also the effect of all these upstream disturbances coming and hitting this, and even the in-service deterioration of the blade, which affects the flow. So now, how can we run just this blade, and how can we account for all these effects, right? So how can I generate, how do I know like how much of turbulence is actually generated by all the upstream components? I didn't simulate it, right? I am only looking at one blade, and like I can't I don't have any idea about like how much of turbulence is generated by all the upstream components. So that is still a challenge. Okay, so we are talking about some progress, but as I mentioned, as we move on, this is one of the challenge. Okay, so the current state of the art ways are to synthetically generate some of this incoming turbulence. Okay, so you can use some probability functions, right? So this is called a synthetic box turbulence, wherein you give some value of turbulence intensity, and there is some turbulent length scale over which these fluctuations have to be generated. If you simply give a random noise, it's not going to work, because turbulence is just not random. Okay, so there is a very well correlated data. If you looked at the structures, they have some correlation. Okay, so that's why like we need to have some good tools for generating even this inflow conditions. So you can generate some incoming free stream turbulence. You can also generate some turbulent wakes synthetically. Okay, so these are like some precursor simulation, like in some little region, like where we are going to simulate how the flow could have been. Okay, so how it would be before hitting this turbine blade. It's a guess. Okay, so and all that we have with us is some of these parameters. Okay, so some wake deficit, like the wake width, right? So you have some parameters, and you have to generate that correlated data from that little information. And this is still a really active area of research. And you can also have some boundary layer developing on this plate coming and hitting this blade, right? So to just put it, like we have all these three, right? So we can have some turbulent boundary layer, we can have wakes, and we have some background free stream turbulence, like everything going and hitting that blade, right? And we also want to ensure that the inflow condition is right. And for that, you do some very simple cascade tests. Okay, so in experiments, what people do is they are not going to have an experimental setup for the entire portion upstream of the engine, right? So they would simply put like some sort of like a moving bar mechanism up front, right? So some cylinder which keeps on, like moving from top to bottom, which will shed the wake. So that cylinder itself is the representative of some, like a upstream rotor, right? So it will generate that effect. Okay. So all that we can do to check this, if the CFD simulations we are doing are right or not, is to set up miniature, like small scale experiments and see that our simulations are doing a good job. Then, like use this validated solver to explore more and more parameters, right? So that is the typical, chain like which we are actually following, right? So here we can clearly see, so these were some of the measurements done by Dr. John Cool in Whittle Laboratory in Cambridge. So he was an experimentalist, and he was, he carried out experiments. I carried out the corresponding simulations for this. So we can clearly see that as the wake is passing, we see the decrease in the velocity, we see the increase in the turbulence, right? So as the wakes are moving upfront. So here, there are some simulations of, how the flow is behaving under different conditions. So if there is no upstream disturbance, everything looks smooth. Whereas when you put some free stream turbulence upfront, right? So you have some turbulence coming from above, you see some sort of spots developing here. If you look at this roughness, you very clearly see that there are some streak sort of structures which are formed here. And when you have this wake, which is a periodic disturbance, you will see once the wake hits the blade, you will see strong disturbances coming. Okay, so let me play that. Yeah, you will see the strong disturbances. This is because of the upstream rotor disturbance hitting this stator disturbance, right? So that gets convected. Now there will be another disturbance coming. Yeah, so this is another disturbance. So that is the wake which is traversing down, right? So we have this sort of disturbances propagating. And now in the experiments, they had some optical access where they can see the qualitatively how the flow is behaving. So I was also able to, compare the qualitative behavior just at the transition location. So somewhere here, okay? So before the wake disturbance passes, the scenario is transition location is somewhere here. Before that, it's just some pre-transitional fluctuation. Downstream, you will see turbulent characteristic. Then you see some typical spots as seen in the experiments. These are called some path span KH. I'm not going to get into details. And as the wake disturbance sweeps through it, you see the transition point has completely moved upstream, right? So it's not just qualitative, you will see a quantitative comparison also. There were some pressure tabs which were used to monitor the velocity distribution, pressure distribution over the plates and the blade, etc. And how the losses downstream of the blade were varying with time also. Okay, so the basic idea is the numerical framework is validated against the experimental data. So you can very clearly see the same sort of thing happening over the turbine blade, right? So here, we have a turbine blade and we have a laminar flow. There is a little flow separation. There is this transition to turbulence. These are the Kelvin-Helmholtz vortices, and then there is a full turbulent flow. And this is the wake disturbance coming and hitting. So that wake disturbance is traversing. This whole coherent structures are gone, right? And then once the wake is gone, it gets back to its original, flow, right? And what happens in terms of the bubble, right? So there is a separation, right? So here, yeah, so I think this is not playing in full screen for some reason. Okay, so what you can see here is as the wake is passing, so before the wake passes, the bubble is, large. But as the wake is passing, the turbulence from the wake trips this bubble and the bubble entirely suppresses. Okay, so it becomes really small. Okay. And then, again, once the wake has passed, it again regains its original size back. Okay. So that is what is happening in this process. And the bottom line is if you didn't account for any of these upstream disturbances, you would say that the bubble is this big, okay? And the losses, whatever you are you will predict from the turbine blade are so huge, okay? But as you keep adding more and more realistic features into it, say free stream turbulence, roughness, and wakes, then this is the size of bubble which you would actually see in an engine, okay? So it is very, very crucial to mimic the kind of conditions which this blade actually sees in an engine. Okay, so and what we see from this is the total loss, whatever you generate downstream of this blade, is the momentum loss, right? So you are actually tripping the boundary layer much more early because of all these disturbances. The boundary layer is getting tripped early, so the boundary layer will be thicker. So that is something where you are losing the performance, but you are gaining the performance by making this bubble shorter. Okay, so there are two things. One is adding, like one favors you, the other is not favoring you, right? But in the case of low pressure turbine blades, we see that whatever benefit we get from the bubble suppression is much more than the just this boundary layer thickening. Okay, so in fact, like what the study also shows is, if there is little bit of roughness upfront, it is actually helping. In the context of this high lift turbine blades, that roughness literally acts like some trip and it can eliminate the separation. So our concern was, like we had a big separation, right? So the modern design had a big separation. But if you had a as-cast surface blade, like you don't want to polish way too much, like the blades from aerodynamic perspective. I'm only talking from aerodynamic perspective. So if you make it really smooth, then, like you lost that little benefit which you actually get from roughness in terms of suppressing the separation bubble. Okay. So we clearly have shown, like, and then the experiments also confirm that this roughness actually helps in the context of high lift, low pressure turbine blades. Okay. So, but surely roughness will not help you in the case of high pressure turbine blades. So you should use like some of this result. This is not like a universal result. Okay. So in a specific application, you see the benefits. Okay. Right. And now, okay, yeah, we have generated all this data. Like, how can we utilize that to in the bottom end of the pyramid, right? So what we have done is resolving turbulence. But on the bottom end of the pyramid, we can model the turbulence. Okay, so if you model the turbulence, like if you simply use the K omega model and do this problem, you will see a massive separation bubble, or based on your inflow condition, like it will be a simple attached flow. Okay, you will not see, like, whereas what the LES gives you is this. Okay, this is the size of the bubble. A K omega model can, predict a massive bubble, or if you have already, like use the fully turbulent condition, like it will just give you an attached boundary layer. Okay. Whereas now you can use the information. So this is missing all the streaky structures, right? So up here, you see this green bit, right? That is all coming from the streaks, like whatever the upstream disturbances have generated. So that is entirely lost in this model. Okay. So because now we have this high fidelity data, we can also, come up with some different fancy models like this laminar kinetic energy, where we gradually take this minus R, like we are taking the energy from the laminar portion and we are adding that to the turbulent kinetic energy. So that gradual transition is going to happen. Okay. So, and that is what you are seeing, that we are actually getting back that green bit and we are again regaining the size of that bubble, etc. Okay. So, but obviously, like this LES, as I told, in terms of accuracy, it is great, but it takes a week to run. Whereas this laminar kinetic energy approach, once you use that LES information, it takes only half an hour to run. Okay. So this is one little case study. The other case study is, say, the intake fan interaction. So the modern aircraft architectures, they are all like going towards high bypass ratio. So if you have really high bypass ratio, it means like, which means like you make this diameter much larger. It is obviously good from aerodynamic perspective, because like from propulsion perspective, because you are breathing in more air. Okay, and the amount of delta increment, like m dot v, that thrust whatever you are going to generate is going to increase. And there are obvious benefits in terms of fuel burn, and it will reduce the emissions, noise, etc. So there are many interesting aspects, like as you increase the bypass ratio of the engine. However, on the other hand, because the engine is much larger now, the weight is going to increase, the surface area has increased, which means the drag on the surfaces will increase, right? So there are a lot of other issues. So in order to minimize these issues, the modern engines are trying to cut down the length of the engine. So this green is the modern engine intake, and that blue and red are the, like typical candidate engines which you might see in the future. So you can very clearly see we are cutting down on that area, right? So we are reducing the length of this intake. But what is the problem? This intake clip is getting more and more closer to fan. Right? So we have this intake lip, but like there is not enough room for the flow to stabilize and like the turbulence to come down and then like smoothly get into the fan. So this intake aerodynamics is going to very tightly get coupled to how the fan behaves, the fan performance, right? And on the other hand, the fan also does some, like it has an impact on how the intake dynamics actually behave. These two are now way too close, okay? And that is the solution is to basically, like make this shorter and this lips to be slimmer. However, like we have, like particularly like during takeoff, we can have some local shock and there is a massive separated flow. Once the separation is there, like separation is always bad for the downstream components. We want to avoid any, unwanted separations upstream. So that separation basically hits the fan face. So this is under high incidence. And under strong crosswinds, like you will have separation on the side lip, right? So if the flow is coming like that, again, it's not that, like the flow will always come straight, okay? There can be a component to that. So if the component is basically higher, which is in fact the case, like during high incidence, like during takeoff, the engine is at some angle, right? And then under crosswinds, like you can't predict crosswinds. So, during landing or during taxiing, you can have severe winds, like blowing, right? And there can be separations happening on that side of the lip. And whenever these separations happen, this can go and hit the fan and they affect the performance. So in order to capture this sort of like thing, like you can always say run full 3D simulations, like this is an unsteady run simulation. And this was run on some 150 million grid points for almost like 3 weeks or so, okay? And on order of 1,000 processes, okay? So you can very clearly see this shock, and then there is a separation. This is the whole distortion. That's the fan blade effect, right? And there is a paper like which we have published, like which talks about all this interactions and how it deteriorates the fan performance. So, but the idea is, like this is taking almost like 2 weeks, and such kind of simulations can't be used for designing the components, right? So we need some sort of economical design to optimize this intake shapes. So that's where like whatever bladeless approach I have come up with, right? So whatever I have introduced previously, recently in the one of the slides, IBM SG, image boundary method for smear geometries. So that kind of approach can be used where you are not going to, like use the resolve the fan. Okay, you are only going to say this is the typical deflection the flow undergoes once it hits the fan, right? So that's what is this sort of IBM SG is basically giving. And the good thing about it is, like you, if you do a blade with blade calculation, and if you do the body force like IBM SG calculation, so that dashed line is the performance characteristic. You get the corrected mass flow, total pressure ratio, and also like how the mass flow is varying radially, right? So all that is agreeing well with the body fitted grid system, okay? So now, like if you do the intake only calculation, you are simply say increasing the angle of attack onto this intake only calculation. Then you see that initially there is some shock. Okay, so at some angle, like you have some transonic flow, local transonic flow over the lip. But as this engine keeps on taking off at a higher angle of attack, then the shock becomes really strong. And this is the separation, okay? So again, this is some validation, again, some experimental data. Now, like if you look at the total distortion at this fan face, right? So there is a separation, right? So there is a flow separated here. You cut this plane and look from this end. Then you will see this as a circle, right? So you have this annular sector where you have the entire loss of stagnation pressure. So stagnation pressure loss is always bad, okay? So this stagnation pressure loss keeps on increasing as you increase the angle of incidence. So here and all, like we have attached flow. So this is one parameter which says how much blue it is, okay? How much loss in P naught we have. So here, like the engine, the aircraft is taking off at a smaller angle of attack, right? So until some angle of attack, it is all fine. It is all very small loss. But all of a sudden, because if you further increase the angle at which this flies, the shock becomes strong and it becomes massively separated. So that is what you are basically seeing here. All of a sudden, at this angle of attack, you see, like a huge loss which is generated. Okay, before this, it would be, if you take a point here, it would be completely, this blue region will be very small. Okay, so there will be nothing actually. Okay, so now this is an intake alone calculation, right? So this is the intake only calculation. But if we look at the coupling between the fan and the intake, then we see that this distortion has decreased. Okay, so the distortion, because of the fan effect, like the distortion actually decreases. Okay, and this is a bladeless calculation. The same thing, like if we run with that 2 weeks, right? So we have spent 2 weeks, that full animation, whatever I have shown, like this is the solution which you get with blades. Okay, so this bladeless approach, we're using immerse boundary method for smear geometries, it runs in 2 hours, whereas the one, like the full unstudied RAM simulation, is going to run in 2 weeks. So this is our design tool now, right? So once we have this kind of design tool in place, we can obviously, like play around with, I have a intake here. There is no fan here. I can place fan anywhere I want. In a day, it's done. Okay, I get the full distortion plots, right? So I say when it's intake only, like then the distortion is, like much higher. Whereas as I bring the fan closer to the inlet plane, then I'm actually clearing off the distortion. Of course, on the other hand, the fan performance is getting affected. That also, like we can get an idea from some of the simulations. Okay. So now the other simple case study is this control. Like, I was interested in, can we control some of the separations, right? So in order to check that, like there is here there is a low speed separation. Here it's all low velocity, right? So separation is characterized by low velocity, like you have reverse flow, right? So you have a negative velocity. But what if you put a device here which is going to energize that low speed velocity flow? It is going to push that flow. It is going to generate a forward, like high velocity, which is going to clear off that separation, right? So if we have such kind of a device, can we suppress this separation? So that is the idea, and plasma is something like which can do that. Okay, so it's a electrode. You have 2 electrodes. You have some dielectric separating it. When you give some AC voltage, you will generate plasma, and this generates some body force. Okay, so you will basically, with this simple setting, like you can generate some sort of like a body force. So this is the force which we want to keep somewhere there, right? Such that that force is going to act on the low velocity fluid and energize that flow and clear off the separation. Okay, so there are variety of approaches to model this plasma, and some of the source terms, etc. Let's not get into details. But one important quantity which you will encounter, like Reynolds number, which is inertial to viscous, like there is an important non-dimensional parameter called DC, which is the ratio of how much electricity you should give to how fast the flow is, right? So electric force to inertial force. So now it's a CFD simulation, right? So I simply played around with that number. Oh, I don't think this is playing. Sorry about that. Yeah. Okay, so this is not linked. Sorry about that. But what this animation is supposed to show you is as you keep increasing to 168, you should have seen a very simple, like attached flow. Okay, so let me go back to the one of the slides. You see this plasma flow control. So initially, like at low values of plasma, you will see a much higher separation. Whereas once you inject more and more plasma, it becomes entirely attached. Okay, so that was supposed to be an animation, but it didn't work. It's fine. Yeah, sorry. But in CFD, like I can keep on increasing that parameter, not a problem. But practically feasible value is only 25. So this is way beyond the reach of experimentally making this actual thing work. Okay. I told about the tonal noise. Whenever the fan wake comes and hits this sort of like blades, you generate noise in all the directions. You will also generate some interstage noise, etc. So again, like you can run some massive simulations which use high performance computing, and then you put some probes to collect the pressure signal. You take some FFTs of the probes, right? So you put some probes upstream of the rotor, downstream of the rotor, in the bypass duct, in the core duct, within this interstage region, right? So you can put so many probes in the simulation. You get some pressure fluctuations, and from that, like, you can get what is the pressure fluctuation like, and convert this pressure fluctuation into sound level. Okay, so you can predict such kind of tonal noise, and you will see very distinct peaks. Okay, so you will see very distinct peaks because the number of rotors are fixed, right? So the number of wakes which are coming are fixed, right? So it's everything like it's a tone. If I do tuck, 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 you are actually hearing a tonal noise there. If I do zzz, sort of like a sound, that's a broadband noise. Okay, so in tonal noise, you will see these sort of like very distinct peaks in the frequency. Whereas the other important component of noise is the jet noise, wherein, you know, like, you generate a lot of shear layers, right? So this is downstream of the nozzle of the aircraft, like, right? So you see a lot of shear layers. There is a lot of turbulent mixing happening. Okay, so there is so much of mixing. You have all the shear layers mixing, and you have a lot of turbulent structures, all the vortices, whatever I have shown in a lot of videos till now. And those also will generate pressure fluctuations, which generate the sound. Okay, and that is a broadband sound. Okay, so it will not be like tuck, tuck, tuck sort of sound. It will be just like a zzz, sort of like a broadband sound. Okay, and even that is annoying. Okay, so you can very clearly see how the pressure fluctuations are actually traveling. And here you don't see any specific spikes in the spectra. Okay, so you can also capture the broadband noise. Okay, so that is all about the progress. And finally, I know, like, I have some 5 minutes left, and which is sufficient enough for challenges. Okay, so we already discussed a number of challenges as we have moved on. And I will just show some examples of what additional challenges, you know, like, we have. And this is not an exhaustive data set. Okay, so obviously, like, when we are talking about such a powerful machine, you have to pay for electricity, cooling, and maintenance. And the CDAC facility which we have, like, when I went there, like, they were saying that they spend around like 1 lakh rupees per day for all these aspects. Okay, so it's a huge amount of cost, like, which is basically involved in maintaining such kind of a facility. And of course, like, you will get, you know, like, we discussed about all this resolving, modeling, etc. And the more we are resolving, the more accurate it is, but we are generating huge amount of data, right? For a simple, like, rotor stator simulation, I would generate some terabytes of data. I keep on buying this hard disk of terabytes, and, you know, like, we keep on storing that data. And how can we, like, what can we do with that data? And the latest trend is to use the machine learning, right? Machine learning algorithms on this big data for turbulence modeling. So basically, like, we have generated huge amount of spatiotemporal data, and we want to feed this data from these models to fix any inaccuracies in the turbulence models. Okay, and even to do this, we need again HPC. Okay, so this is like a loop now. Okay, so whatever data we are generating, we are again using HPC, but testing the, you know, for training the machine learning models and for testing the ML models, which again, you know, costs you the electricity, etc. And the components which I have shown are very, you know, like, simple, but here you have a high pressure turbine blade, right? So which sees around 1700, 1800 Kelvin, right? Which is way beyond the melting point of the blade. So you have a lot of advanced cooling technologies over that. And how can we, you know, like, mesh all these things and, you know, like, create, like, study all these passages, etc. Right? So it is not just the aerodynamic perspective which we should be worried about. We should also worry about the aerothermal and aerostructural issues. Okay, so that's altogether a completely different domain. Okay, and I already provided you an idea about, you know, like, I gave you an idea about why it is crucial to give some realistic inflow conditions, whatever you encounter in the simulations. And it is very difficult to measure these things experimentally also. Okay. Then there are load balancing issues, right? So we want to distribute, each computer should get its own share of work, but it is not always possible to give the same amount of work to all the computers, like equal amount of work to all the computers. Okay, so for example, in this high pressure turbine blade, like turbine rotor has some mesh, turbine stator has some mesh, cavity, cooling hole, seal, like the amount of mesh which you put in these regions completely differ, right? So if you know, like the turbine rotor is a massive mesh, then you know, like that is the bottleneck, right? So that takes longer, whereas all these smaller ones are going to finish computation quickly. So we encounter load balancing issues. So that has to be minimized. And if you some of the codes they have this fancy feature of adaptive mesh refinement, which is a great feature. So you as the flow is evolving, the mesh is going to adapt itself, right? So it is going to, you know, like wherever the gradients, wherever the vortices are more, that's where you dump more mesh. But again, this poses challenges for you know, like how am I going to split this domain decomposition? How am I going to do this across different processes, right? So it shouldn't be like one processor is taking a lot of time, whereas all the other processors finish their job and waiting for the communication from the other processor, right? It should not happen like that. So finally, yeah, there are some things like you can have a RAND simulation here, you can do some LES here, and how do you generate some realistic turbulence data across this interface is one more pressing topic. And I also mentioned that high order schemes are much better. You can cut down on the number of grid points. But high order schemes are great if you are actually, you know, like trying to capture all the turbulence there, turbulent boundary layers, all those things, right? But when it comes to shock, you end up with something called a Gibbs phenomena, and they become unstable. So stability is another key criteria, right? So high order schemes are great for turbulence, but not for, say, shock. So how do you handle these kind of things? So there are many more challenges in this front. Okay, so I'll skip the solver development. This is something which we were doing in-house, and you know, like all the different features of the solver, validations, etc. So I'll skip them. And to summarize the talk, you know, like we looked at the turbo machinery, a brief background, restricted ourselves to aircraft engines. We looked at different simulations. What are the options for modeling the flow, options to model geometry, grid requirements? What was the progress in terms of HPC, and some of the case studies on turbine, fan intake interactions, etc., and plasma flow control, etc., and tonal noise and broadband noise, and some of the challenges like which we encounter still. You know, like there are many more challenges actually. And I would like to acknowledge, you know, this is not my single effort. You know, like everyone like who has provided me funding, and my team at IIT Madras, and also, you know, collaborators at Cambridge, Rolls-Royce, and Melbourne, and hackathon events for, you know, like GPUing my solver and, you know, speeding that solver up, etc. So I thank all this like CDAC, NVIDIA, OpenACC, and ISEP Pune for that. And thank you very much for your attention. Sorry if I had rushed in between, but I thought like I hope like the big picture has been communicated properly. Okay, so I'm happy to take any questions. Thank you.
Thank you very much, sir. Any participant having any question, he or she can ask. Yes, anyone having any query or question?
Yeah.
Yeah,
Good afternoon,
yes.
sir. This is Anand.
Yeah.
Sir, in one of your slides, I saw some short form like FST, ROU, FR, FW, BIW.
Yes,
So, can you just brief about it?
Yes.
What is
Yes.
it?
Yeah. Sure.
Thank you.
It's a different combination of the upstream instabilities like which I had put. Okay, let me go back to that slide. I think this is the one, right? No, next, this one. Okay.
Yeah.
So LAM is laminar inflow, like where there are no disturbances. I told like there are 3 different disturbances, right? Free stream turbulence, wakes, and surface roughness on the blade, right? So if it's a laminar flow with a smooth wall, like there is no incoming free stream turbulence, there is no incoming wake, nothing. So that is a laminar flow. Okay. FST is just free stream turbulence alone, right? So we only have the free stream turbulence. The second one is we only have the roughness. Okay, so only the blade is rough, but without any free stream turbulence. FR is a combination of these two. So I have put free stream turbulence over a rough wall. That is this. And the next one is I have free stream turbulence and wakes, right? So I have the periodic passing wakes. Then FRW is I have put all the three: free stream turbulence, roughness, wakes. Does that clarify your question? Yeah.
Yeah, sir. Yeah.
Okay. Yeah. Thank you.
Yes, any other participant having any question?
Good afternoon, sir.
Yeah. Good afternoon.
Sir, in your slide, I saw machine learning. What is the use of machine learning in CFD, sir, and artificial intelligence?
Right. Okay.
Sir, voice is not
Sir,
coming.
your voice is not coming.
Hello.
Your voice is not coming clearly, sir.
Hello.
Hello? Sir, your voice is still not audible. No, sir, it is still not coming.
Sir, one time plug out, sir.
You can, sir, try to plug in and plug out your earphone.
Yes. Is it better now?
Yes, sir, it is coming.
Yes, sir.
Yes,
Okay,
audible,
fine.
right?
Yeah. Thank you. Yeah. So the idea about so in order to understand like how the machine learning can be used for, turbulence model in particular, we should know like how basically turbulence models are developed, right? So if you take your Navier-Stokes equations and you do something called Reynolds averaging, right? So you decompose the signal into mean and fluctuation, right? So you have a U prime. You are writing any quantity U as U mean plus U fluctuation, right? So when you plug that kind of decomposition into the Navier-Stokes and do prime averaging, you end up with some unknown terms. Okay, so there will be some, it's called a typical closure problem. So you have some terms in the Navier-Stokes which you don't know, which you can't close. And in order to close those terms, people came up with so many different approaches. Like say, what is it? One equation, zero equation, right? So you have Spalart-Almaraz, K omega, K epsilon, etc. Right? So you have so many different models which are totally focused on, like how to close those terms, right? But with machine learning, what you can do now is to close those terms, people were looking at some empirical data, very, they would do some experiments. They have very few measurements data, right? So they have very few measurements. And then that is what they were using to fit the different constants in your turbulence model, right? So if you look at Spalart-Almaraz model, right? So you would see some very weird, random constants coming into picture, right? So now with so much of resolved data, you have much more information to actually fine tune these constants, or in fact, like even trash some of the Bosnisk approximation, like linear stress strain relations, etc. Like you can throw them off, and you can accurately model the leftover terms coming in the Navier-Stokes equations, right? After this Reynolds averaging. So I'm not sure like if I have conveyed this point properly or not, but the whole idea is like you want to get rid of the turbulence models and or put more generic terms based on so much of huge data set which you have actually obtained, right? That is a broad way in which this ML works. Another way is ML is really good with predicting the future snapshots. Okay, so suppose I have given you a lot of images, right? So I have played a lot of animations, right? So you have so much of data, so many snapshots. Like I made a video out of it. I played that video, right? So machine learning can learn from these set of snapshots, and it can predict like what is going to happen in the future. You see what I mean, right? It's like traffic, right? So you have taken a lot of how the traffic is moving in a like a camera. You have captured it, and then like there are a lot of ML algorithms which can say how the future of like how that vehicle is now going to take a turn, right? So it can actually predict the future snapshots of that. So exactly those kind of logics can also be used for say like this kind of simulations, right? Does that answer your question?
Sir, CFD is also used in data science for predicting the data analysis.
Can you repeat that question? I don't think I got two words. CFD is used in data science. Huh?
Yes, sir. It is used in data science for predicting the data or not.
So what do you mean by that? Like I don't think the question is clear to me. Like for predicting what data?
For like simulation or any type animation type.
Yeah. So you will use like you will use the solver, CFD solver, to generate all this animations, right? Yeah. So from running the CFD solver, you already got the data. Now on this data, like you apply the machine learning algorithm to predict the future snapshots. Does that make sense? So the way your question was the other way around. Does CFD use the data science? I don't think like I got that right. Maybe you can be a bit more clear.
Sir, I'm saying that CFD in future, it is more used in data science, machine learning and artificial intelligence.
Yeah. Obviously the data which you are developing from the CFD will be used to enhance the CFD feed. That is surely happening. It's not like happening in the future. It's already it started like 7-8 years back, and even before that it started. But because of the HPC, this also it's a very active area of research.
Then there will be any HPC role in the coming generation, sir? In coming
Yes, absolutely. Like as I mentioned, like even for machine learning or to run your ready resolving simulations, which are much more accurate, HPC is a must. Okay, so there is no way like you have to like we are totally relying on the high performance computing.
It means, sir, that in machine learning and means machine learning, data science, and artificial intelligence, they all are interconnected with each other.
Yes,
and it is help us to predicate the data very fast.
That's right. Yeah.
Thank you, sir.
Yeah. So it's called data-driven modeling. It's no more a turbulence model. It's called data-driven modeling. Data-driven modeling. So data from high fidelity simulations is driving your model. So data-driven modeling. DDM.
Sir, it is now applied in all our R&D fields.
So I know like quite a few teams across the world like using it. So this ML is not restricted only to CFD. Okay, so it's in other fields it's already like getting used a lot. Okay, so but in CFD like I know like it's getting used in Rolls-Royce. I saw papers from GE, right? So it is quite an active area. So over the last 2-3 years, if you look at any ASME conference proceedings, like there are so many papers on machine learning coming up. Yeah.
Okay, thank you, sir. Thank you, sir.
So most of the, sir.
Yes, continue.
Yeah. So most of your studies which you saw are related to turbine. Are they all cold study or hot studies, sir?
These were all cold study. I didn't look into the heat transfer aspects. Like my colleagues did look at some impinging heat transfer and etc. But I didn't look into the because I was focusing mainly on low pressure turbines where the temperatures are like thermal related issues are very minimal. Those who are looking at HPT, like combustion chambers and like turbine coupling. So those are the studies like where thermal effects are much more important.
Yes. And so nowadays, people who are working in the domain of turbines, they are because of the lack of facilities, high performance computing facilities, they are also using for the turbulence modeling. They are using SST gamma zeta turbulence model. So
Yes.
can you Can you please?
Yes. So it's a so gamma RE theta model or laminar kinetic energy model. Like there are a variety of transition models, which are all again based on empirical data. Okay, so it is not like these are like it's not like they will work accurately for all the test cases, because the way these models have been developed are based on some empirical data, which is some experimental data which was available with them, right? And then the constants have been tuned, and they will work absolutely well for those particular applications. But the moment like you encounter a new kind of physics, then these models will break down. Okay, so that is the kind of that is where we are moving more and more towards universality of the model. Okay, but it's absolutely fine, like if you are using some gamma RE theta transition model, different transition scenarios, these are all well tested for some of these applications. But if the flow is accelerating so much, or if there is a sharp curvature in your domain, right? So under such conditions, or if you have some surface roughness effects, right? So under those conditions, these kind of models will fail. Okay, so you should be careful while choosing.
Okay.
So all models are wrong, some are better, right? So I think that is the same. Yeah. But they are better. Like they do the required job. That's
okay. And so one last question. So in the case of smeared geometry, do the designers take care about the design aspects like the free vortex law and other?
Yeah, so because the way the smear geometry works is based on the mean camber line. Okay, so as long as you are you take care of that mean camber line, your radial work distribution is taken care of. No issues.
Yes. Thank you so much, sir.
Yeah.
Yes, any other participant having any question? Anyone? Okay, then thank you, Dr. Rao. On behalf of Mechanical Engineering Department, ADIT, I thank you for accepting our invitation and delivering a talk on such a challenging topic that simulations of turbo machines and high speed computation is a challenging task. So you have covered it really nicely. You have answered all the questions really nicely, sir. So thank you very much, sir.
Thank you very much for giving me this opportunity. Yeah, I hope you all liked it. Thank you.
Sure, sir. Thank you.
Have a nice day.
Yeah, thank you, sir.
Bye.
The second session of our last day will start at 2:30 p.m. and the valedictory function will start from 3:45 p.m. onwards. The link for quiz and feedback will be shared during the valedictory function. So all are requested to remain present in last session as well as in the valedictory function. Thank you everyone.